In this video, we'll be looking at physical and spectroscopic properties of some carboxylic acid derivatives. As we consider physical properties of some carboxylic acid derivatives, we're going to focus on boiling point. With our first column here to compare, we're talking about London dispersion forces or induced dipole interactions, dipole-dipole interactions, and hydrogen bonding. Because we want to compare different types of intermolecular forces, we should use compounds that are similar size. So let's check. This has a molecular weight of 72 grams per mole. This is 74, and this is 74. And the boiling point is 28 degrees Celsius, 57 degrees Celsius, and 99 degrees Celsius. So esters, having dipole-dipole interactions, intermediate in terms of strength, stronger than induced dipole, not as strong as hydrogen bonding, and the boiling point reflects that. For our next series, once again, we're talking about different types of intermolecular forces. So let's check on the molecular weight. This is 56 grams per mole, 58, 60, 59, and 55. About as close as we can get. And the boiling points are -7 degrees Celsius, 56, 82, 221, and 97 degrees Celsius. So London dispersion forces compared to dipole-dipole compared to hydrogen bonding, we see the expected trend in boiling points. If we compare the dipole-dipole interactions of this ketone and the dipole-dipole interactions of this nitrile, we must be talking about a stronger dipole because this boiling point is significantly higher than this one. What's most noticeable is the difference between these two compounds. They're both capable of hydrogen bonding, but this one is capable of more hydrogen bonds. And we see a difference of boiling points of 82 degrees compared to 221 degrees. So clearly, these intermolecular forces are much, much stronger, which gives this compound such a high boiling point. And with our last column of comparison, these are all amides, and this time we're not looking at the same size. This one is 59 grams per mole, 73 grams per mole, and 87 grams per mole. So typically, as we are increasing in size, we also increase in boiling point. But here we have our boiling point of 221 degrees Celsius compared to 206 and 165. So although we are increasing in size, we are decreasing the number of hydrogen bonds, so that here there's no hydrogen bonds possible, and therefore the boiling point decreases. Other physical properties such as melting point or water solubility, these will also follow the expected trends depending on whether we have dipole-dipole interactions and the capability of accepting hydrogen bonds or the directability to hydrogen bond as well. As we consider the spectroscopy of a number of carboxylic acid derivatives, we can consider, first of all, IR spectroscopy. And in general, whenever we're talking about a carbonyl, the focus is around 1700 inverse centimeters. But in this table, we have some specific frequencies for some specific types of compounds. And I want you to be aware that there is quite a range. Notice though, if we have a ketone or an aldehyde compared to an ester, in many cases, the range for the carbonyl is going to overlap. And so just looking at the carbonyl absorption, it's often going to be difficult to determine whether we're talking about an aldehyde or a ketone or an acid or an ester. In some cases, there are things that stand out. For example, if you have an acid chloride, this absorbs much higher, so at about 1800 rather than 1700. Or if we have two significant absorptions, both significantly higher than 1700, then this points to an anhydride, for example. But in other cases, rather than trying to distinguish exactly what type of compound it is based on the carbonyl absorption, it's more helpful to look for other features. So for example, if we have an ester, we would want to be on the lookout for a CO single bond. If we have an amide, we would want to be on the lookout for a CN single bond and possibly an NH bond. So it's important to use IR to find a carbonyl. In some cases, you can use the carbonyl absorption to get more specific, but often it will be other IR features and other spectroscopic features that will help you to distinguish acid from ester from amide, for example. If we consider proton NMR spectroscopy, we want to think about the hydrogen that's connected to a carbon that's connected to a carbonyl, and whether this carbonyl is connected to a chlorine or a nitrogen or an oxygen. We're still talking about these hydrogens showing up around 2 to 3 ppm. Depending on the type of carboxylic acid derivative, keep in mind if you have an ester, then you're looking for these hydrogens around 3 to 4. For an amide, these hydrogens would show up also about 3 to 4, but the NH of the amide, these vary and they can show up typically between about 5 to 8 ppm. And finally, when we're thinking about C13 NMR for carbonyls, I like to consider about 200 ppm, but this really applies more to aldehydes and ketones. Carboxylic acid derivatives is going to be a little bit lower, so closer to 170 ppm. In some cases, this may overlap in the aromatic region, and so it's important to look at all of your data combined to be able to interpret your spectra. In C13 NMR, you also want to be on the lookout for the other carbons of the carboxylic acid derivatives, such as the carbon next to the oxygen in an ester, or the carbon next to the nitrogen in an amide. Now that we've reviewed some basics, let's take a look at a couple of examples. Here we have an IR and proton NMR spectra for an unknown compound. Looking first at the IR, what should jump out at us? Here just above 1700, this is an absorption for a carbonyl. And over here we have another really strong signal. This looks like it could be a C single bond O. Since we don't have a carboxylic acid OH, then this suggests we might have an ester. In addition to 1700, we always want to look at 3000 as another magic number, and peaks that show up just below 3000, these are typically due to sp3 hybridized carbon connected to hydrogen, so the sp3-CH stretch. Next, if we look at our proton NMR spectrum, let's call this signal A, B, C, and D. A integrates to 2, so it must be a CH2 group. It shows up at about 4 ppm because it must be next to an oxygen, and it's a triplet because it must be next to 2 hydrogen neighbors. Looking at signal B, this integrates to 3 hydrogens, so this is a CH3 group. Because it's a singlet, we know that it has no hydrogen neighbors, and because it shows up just above 2 ppm, we know that this is probably next to a carbonyl. Signal C is due to a CH2 group because it integrates to 2 hydrogens. It's not especially de-shielded, and it looks like perhaps a septet, so we know that it has a lot of neighbors. And finally, signal D, this is a CH3 group because it integrates to 3 hydrogens. It must be next to a CH2 group because it appears as a triplet, and it's not near anything especially de-shielding because it shows up close to a typical CH around 1 ppm. So if we put this information together, we get propyl acetate. This is consistent with our IR because we have the C double bond O and the CO, and we have a bunch of sp3 hybridized carbons connected to hydrogens. This is consistent with the NMR because this would be signal A, B, C, and D. This one we would expect to be a singlet integrating to 3 hydrogens around 2 to 3 ppm, and that's what we've got. This one we would expect to integrate to 2, to be a triplet because of 2 neighbors, and to show up around 3 to 4, and that's what we've got. This set of hydrogens would have a lot of splitting because we have 5 hydrogen neighbors, so we would expect a sextet. Remember, we can't always see all of the little peaks, but obviously there's lots of neighbors, so that's consistent with this one. And finally, we would expect this one to show up pretty close to 1 ppm because it's pretty far removed from anything deshielding. We would expect it to integrate to 3 hydrogens, and we would expect it to be split into a triplet, and that's what we've got. Here we have an IR, proton NMR, and C13 NMR spectra for an unknown compound. This would be our C double bond O. Looking at our other magic number of 3000, it looks like we have some sp3CH as well as some sp2CH. And if we look a little more closely, this could be a C single bond N. Not quite as strong as a C single bond O, but it does stand out among other absorptions in the fingerprint region. Next, if we look at proton NMR, let's lump all these together as A, B, C, and D. A, this is in the aromatic region. It integrates to 5 hydrogens, so it must be a benzene with only 1 substituent. B integrates to 2 hydrogens, so it must be a CH2 group. It is a quartet, so it must be next to a CH3. And it absorbs at about 3.7 ppm, so it must be next to something that is especially electron withdrawing, such as a nitrogen. Signal C integrates to 3 hydrogens, so it corresponds to a CH3 group. It's a singlet, so it has no hydrogen neighbors, and it shows up around 2 ppm, so this could be next to a carbonyl. And finally, signal D, it integrates to 3 hydrogens, so this must be a CH3. It is close to 1 ppm, so it's not next to anything especially deshielding. And we see that it's a triplet, so it must be next to 2 hydrogen neighbors. And looking at our C13 spectrum, this would correspond to a carbonyl. These would correspond to aromatic carbons. We have 4 signals in the aromatic region, and then these would correspond to sp3 hybridized carbons. So if we take all this information and we put it together, we can start with benzene. Benzene must be next to the nitrogen because we only have one set of hydrogens next to the nitrogen. So this would be next to a CH2 that is next to a CH3. We also know that we have a carbonyl and it's not connected to the benzene, so it must be connected to the nitrogen. And it's also connected to a methyl group. From our IR, we see the sp2CH and the sp3CHs. We see the carbonyl and we see the C single bond N. From proton NMR, these hydrogens would all correspond to A. Notice these would be equivalent to each other, these are equivalent to each other, and this is distinct, but they're also similar that they're overlapped on top of each other. This would be B, this would be our singlet C, and this would be D. For our C13, if we call this A, B, C, D, E, and then F, G, and H, this carbon would be signal A. In the aromatic region, we have 1, 2, 3, 4 aromatic signals. So these would be B through E. And then we have 3 sp3 hybridized carbons, so that would correspond to F, G, and H. Here's another representation of this compound. So we have an acetyl group, and this would be aniline, and then the nitrogen is substituted with an ethyl group. So this compound is called N-ethyl acid analide. N-ethyl acid analide. Let's consider the spectroscopy of nitriles. By IR, what we're looking for is the nitrile carbon, which absorbs around 2250 inverse centimeters. These tend to be really sharp, medium weak strength, And it could be a little bit hard to distinguish them from a carbon-carbon triple bond, but the carbon-carbon triple bond, they tend to be just a little bit lower, closer to 2150, but you may have some work to do to distinguish between them. For proton NMR, if we are looking for a hydrogen connected to a carbon that is connected to a nitrile, these tend to show up around 2 to 3 ppm. And for C13 NMR, the nitrile carbon tends to show up around 120 ppm. Next, let's take a look at an example. Here we have the IR, proton NMR, and C13 NMR of an unknown compound. This signal right here corresponds to the C triple bond N. Our magic number of 3000, we have peaks just below, which corresponds to sp3 hybridized carbon-hydrogen stretch. And there's nothing else particularly important in IR. Next, if we look at the proton NMR spectrum, signal A is a CH2 group. It must be next to a CH2 because it is a triplet, and it absorbs at about 2.4 ppm, so this could be next to the nitrile. Signal B is a CH2 because it integrates to 2 hydrogens. It is a sextet, so that means it has a lot of neighbors, and it's just a little bit deshielded, so it must be kind of close, but not directly connected to something deshielding. And finally, signal C, this would be a CH3 group, and it's a triplet, so it must have 2 neighbors, and it absorbs at 1 ppm, so it's a typical CH. Looking at the C13 spectrum, this would be our nitrile carbon, and then here we have 3 sp3 hybridized carbons. So putting all this information together, we have butane nitrile. In IR, we see our sp3CHs and our nitrile. In proton NMR, this would correspond to signal A, B, and C. And in C13 NMR, this would correspond to A, B, C, and D. To get better at interpreting spectra and identifying compounds, it is really important to keep practicing.